about projectile motion. The key to projectile motion is simply remembering that gravity only affects the y direction. You never wake up of a morning and gravity jerks you out of bed to the left or the right. It only pulls down. So if we have an object that's fired with some initial velocity v0, like this, gravity only affects the y part of that velocity. So if I break this velocity up into an x component, v0x, and a y component, v0y, whereas we learned before, if this is some angle theta, this v0x is v0 cosine theta, and this v0y is v sub 0 sine of theta. If I break this velocity up into these two parts, gravity can't change the x velocity. Gravity can't accelerate things or decelerate things in the x direction. It just doesn't happen. Gravity can only slow things down or speed them up in the y direction. That's all it can do. So as this thing moves through the air, as it gets here, for example, its x velocity is still what it was to begin with. Its vx is still v0x. But its y velocity, this y component, is less than it was before. And as it gone a little higher here, its x velocity is the same as it was before. But its y velocity is smaller still because gravity is changing the y velocity, but not the x. In fact, when it gets to the top here, its y velocity has gone to 0, but its x velocity is still the same as it was when it first fired. Now that's assuming there's no air resistance. In reality, air resistance does slow down the x velocity, but so we're neglecting air resistance in this. But in as much as we can neglect air resistance, this is what happens. And then as the thing starts falling again, the x velocity still staying the same, and gravity starts accelerating the object, and it's getting faster and faster as it falls. So again, the Vx is just staying the same. It's supposed to be an x, but the Vy is constantly changing, where the total velocity at any part is the tangential vector sum of those two things. Mathematically, here's what we've got. We've got Vx stays the same as V0x, so there's no acceleration in the x for the x part. That just means distance x is just velocity times the time. But in the y direction, our uniform acceleration equations still hold, but only if we deal with y components. Notice this is an x component. This is V0 cosine theta. It's not the total V0. In the y direction, we've got y is y naught plus v naught y t plus 1/2 at squared, where this a is minus 9.8 meters per second squared, and this v naught y is v0 sine theta. You have to use just the y part of the velocities. And similarly, Vy is V naught y plus AT, and Vy squared is V naught y squared plus 2a y minus y naught. So those are our equations for projectile motion when you have something fired in 2 dimensions, recognizing gravity can accelerate things up and down, but it cannot affect things left-right, cannot affect things horizontally. Let me do an example for you. So I'm going to rewrite these equations real quickly off to the side where I can refer to them. I've got distance is velocity times time in the x direction. Y is y naught plus v naught yt plus 1/2 at squared. Vy is v naught y plus at, and vy squared is v naught y squared plus 2a y minus y naught. That's the same equations I had a moment ago. I just wanted to be able to refer to them. So here's my example. Suppose I have a projectile that I fire at 100 meters per second at a 60-degree angle. And I fire it so that it lands up on some cliff. So it does this. It's up there like that. Let me make that dark enough you can see it on the video. And what I want to know is how far back does it hit from the edge of the cliff if the cliff is 20 meters high and the cliff is 320 meters back from where this was launched. There's my example. So what I need to find is x. So this is x. So x minus the 320 will be this delta x. To start with, always find the components, the initial components of the velocity. Anytime you're doing a projectile motion problem, just assume you're going to need those. So v0x is v0 cosine 60 is 100 meters per second cosine 60. That is 50 meters per second. v0y is 100 meters per second sine 60. That is 86.6 meters per second. Because all of these equations have these components in them. Not all of v0, but v0y. Not all of v0, but v0x. Now, to find how far this goes, I've only got one equation that has an x in it. This one. I know v0x, so I'm going to need t. So I need an equation with t in it. This one doesn't have t. This one does, but to use it, I would have to know Vy when the object hits. I don't know that. So let me go to this. When you see my process of elimination here, saying what do I know, what do I need to know? I need to know x, know this, but I don't know that. How can I get that? Let me find another equation. Well, this one has t in it. Maybe that will work. And indeed it does. So we've got y is y naught plus v naught yt plus 1/2 at squared. Y is 20. Y naught, it was fired from 0, is 0. V naught y is this 86.6 plus 1/2 comes minus 9.8 times t squared. And now I've got a quadratic equation. I've already solved that. You know how to solve it. If you work all that out, you get t is 17.4 seconds. So that's when the object hits. So the distance where it hits, x, is v naught xt. Doesn't matter whether I write it v naught x or vx naught. I mean the same thing. So this is 50 meters per second times the time is now 17.4 seconds, and that is 870 meters. So delta x is 870 meters minus 320 meters is 870 minus 320 is 550 meters. Okay. Now, I went ahead and asked another example, another part of this example, I mean. What is v when the object hits? So, what's v? All right, we know Vx is just Vx naught. It's just 50 meters per second. Vy is Vy naught plus AT is 86.6 meters per second plus minus 9.8 meters per second squared times our time, 17.4 seconds. So that is, Vy is minus 84 meters per second. That makes sense because when this hits, it's got a negative y component and a positive x component. So there's V as it hits. The size of V now is Vx squared plus Vy squared square root is 50 squared plus 86.6 squared square root is no, that's not 86.6. Sorry, that's 84. That was 84. I just looked at the wrong number. 84 squared gives me 97.8 meters per second. That's the total velocity here. The angle of the velocity here, theta, is the inverse tangent of Vy over Vx is inverse tangent of 84 over 50, which is 59.2 degrees below the x-axis. So there's my example. You'll get to practice it in your homework. So you'll have these 4 equations now. Always start with finding the components of the velocity, and then it's just a matter of what do I need to know and what do I know, and then using the equations to get those. So they're just puzzles. Enjoy.